Hello everyone. Today we will be talking about the static and fatigue evaluation of automotive suspension control arm. And the agenda we have for today's session is the brief about the suspension lower control arm, the problem statement, geometry description, non-linear material model, boundary condition and load, result and post processing. So in general, the main functions of suspension systems are to connect the wheel to the body, and while going on the road, a lot of road shock and vibration comes to the vehicle, so to absorb the shock to provide the comfortable ride, to ensure the tires are always in contact with the road for a stable handling and steering and braking. So there are two category of suspension system, dependent and independent suspension system. In dependent system, both wheels move together, and in independent system, each wheel can move independently freely. So in modern automotive, you will find mostly independent suspension system where both wheel are moving independently while cornering or any other cases. So there are some common type of suspension systems are solid axle leaf springs, which I think you will generally see in like heavy vehicles, trucks, or the old automobiles. You will find the leaf spring. McPherson Strut, which we will talk mostly about this in this session. Then double wishbone, multi-link and air suspension type of control system. So McPherson Strut is this type of suspension system where we can see there is a spring damper system, and there is a lower control arm. Okay, this lower control arm is there, and there in this part has a ball joint, and with the help of at this location, with the help of it is connected to the tire, and with the bushing joint at these locations, it's connected to the chassis. Okay, here is the similar double wishbone type of suspension system, which is more advanced version of McPherson Strut. So in general, when we are moving on the road, because of the road irregularity, braking, cornering, bump and the potholes, a lot of forces come into our automotive, okay, cars or any vehicle. A lot of forces come into that. So to understand the behavior and the performance of the suspension control arm, we are going to perform some simulation or calculations to understand the performance of suspension control arm. Okay, so for our calculation, we have assumed that our car weight is 150 kg. Okay, and 60% of the weight of car is transferred on the front side. Okay, so because of the presence of the engines and other things, so we have considered 60% of weight of the car is on the front side. So based on that, the 900 kg of weight is on the front side. Okay, and since there are two wheels, so per wheel there is a 450 kg weight. Okay, so each wheel is carrying 450 kg, and if we account for gravity, then each wheel have due to gravity 4414 newton of force acting on that. Okay, so what happens during braking? When we brake, this front wheel stops, and why? Because there is a friction force in this direction, and while braking, a friction force will act in this direction and this will stop. So to calculate the braking force, we can use the friction equation, mu mg, which is the normal force. So based on that, if we calculate, we get a 3531 newton of force acting on the wheel due to braking. But to account for the worst case scenario, because if you are sudden braking or any worst case scenario, we have considered that there is a deceleration of 1.5 g, and based on that, if you calculate mass into acceleration 1.5 g, we get a force of 6621 newton, which is higher than the force calculated from the friction equation. So if we consider this for 6000, this is a worst case scenario. Now second is the cornering. So while cornering, if we see that while cornering, because of the centrifugal acceleration, there is a force acting outward or inward on the car tire. Okay, so there is a force acting in this direction. So we can calculate it by taking 1.2 g acceleration. So based on that, there is this force is mass m into 1.25 g is 5581 newton. So force cornering is acting in this direction, and force braking is acting on this direction. And then we have bump. So due to bump, there is a vertical force due to braking, so which is we have considered 2g. Okay, so this is acting on the wheel 2g, so mass into acceleration, which is 8828 newton. So to account for worst case scenario, if we have added all the forces, force due to braking, cornering and bump. Okay, so this is the geometry of our lower control arm. Okay, so here you can see the dimensions. Okay, based on that these dimensions we have created the geometry in a space claim, and we have performed this simulation. So let us go to ANSYS and see how we can perform this simulation in ANSYS. Okay, so first we go to ANSYS Workbench, and here we have taken a static structural module from this left side to here. Okay, then we have used EN8 steels SEA1045 as a material. Okay, so this is in a grade of a steel. Okay, so we have created the material model by taking the density of a steel, the Young's modulus 210 gigapascal, Poisson ratio 0.3, and then bilinear isotropic hardening in constants like Young's modulus is 350 and Tension modulus is 5000. So how to get the bilinear material model constants? You can refer my previous video, and I'll give a link at the top or also in the description. You can go and see how we can calculate the constants for bilinear isotropic hardening curve. Okay, then to perform the fatigue evaluation, the fatigue parameters, we have also given the life cycle informations. Okay, so we have given the life cycle information, the infinite life at 1 million 260 megapascals, at 3 megapascal we have 1000 cycles life, and at 530 megapascals we have 0 life. Okay, so after that, after creating the geometry and after creating the material model, we can go to ANSYS mechanical by double clicking on the model. Okay, so we have the geometry, and we have assigned the material here EN8 steel SEA10452 the geometry. Okay, now since we do not have any other body, this is a single body, so we don't need to create connections. Okay, and also we don't need to create additional coordinate system. Then we have created mesh on this body. So I have used just body sizing and the global mesh controls to create mesh on the body. Okay, so you can see this mesh can be done better with more controls, and depending upon the application we can refine wherever higher stresses are, but for now we have this mesh to perform the simulation. To set up the braking case, we have created a remote displacement at bushing locations, okay, where we have the remote displacement here and here, okay, and we have fixed x, y, z degree of freedom and rotation about the z degree of freedom for both the remote point, and it is allowed to rotate in x and y, okay. Then we have applied remote force at the ball joint location here, okay, and since this is braking we have applied the force in the z direction, okay, which is friction force direction as explained in the previous. And then we have also non-linear controls on, so in initial step, minimum step, maximum step, large deformation on, okay. So then we have solved it, okay, and we can see the deformation, the maximum deformation is observed at this location. The stress which is maximum we are getting is 78 megapascals, and the y directional deformation, vertical deformation on this due to the braking force is observed maximum at this location, which is 0.15, okay. So this is the static results. Now we can also calculate the factor, safety factor, okay. So this is safety factor based on the maximum equivalent stress and the tensile strength, okay. So this is based on the static strength. To calculate the fatigue results, we have fatigue tool in the ANSYS, okay, and in the fatigue tool we can define different type of loading. So what type of loading we have assumed is a fully reversed loading, okay, and the scale for that is 1. So whatever force we are getting or whatever stress we are getting in the simulation, that will be the maximum used. And then analysis type, a stress life evaluation we are doing, okay, and mean stress theory, Goodman, we have different options, Goodman, Gerber, Soderberg, SME, so but we have used Goodman mean stress theory here. And then a stress component maximum principal stress we have used, okay. So based on that we have calculated the life of the cycle, life of the lower control arm, okay, how much damage we have, and the factor of safety, okay. Yeah, factor of safety, I think we want the design life to be 1 million only, okay. So based on that we can calculate the factor of safety, okay. So this is how we can calculate the static factor of safety and the fatigue factor of safety. And I have for all the cases I have made this presentation with all the results, okay. So this is due to braking, and we see maximum force of 78 megapascals, okay, and the factor of safety due to yield is minimum 4.4 because our yield strength is 350. So the life due to fatigue life is million cycle, and the factor of safety due to fatigue is 3.3, okay. For cornering, the minimum yield factor of safety is 4.69, and due to fatigue it is 3.48. And in case of bump, we can see that due to bump the deformation is 16.3 millimeters, which is very high. Also you can see that due to bump load only we have crossed the yield stress. So at these reasons, the red region, we can see the stress is higher and it's crossed the yield stress. And if you look at the fatigue factor of safety due to yield stress is less than 1, which is 0.9, and the life is also here. In other cases we found that life is 1 million, but in this case the minimum life is 668 cycle only, and the factor of safety here is like very less, 0.6. And if we look for the worst case, so we can see from these results is that the bump load result is dominant, and the similar result we are getting in the worst case also. And again the factor of safety also here is more influenced by the bump load case. So we can see there that this will fail due to the bump, so we have to improve the design of the lower control arm so that it survives our requirement, and our automotive should be able to go through the road performance, better road performance. Yeah, so thank you everyone.